This is 10.2, area between curves in SynMath 31. When we talk about the area between two curves, what we're going to do is use the information, or the ability from 10.1, which allowed us to find the area underneath curves. We're just going to make the definition a little bit clearer. Now, some students, and often anybody reading this, finds this a little bit confusing that all of a sudden we use this capital F prime of x. And the reason we want to do that is because really what we're making is a composite function that allows us to then find the area under that composite function. And the logic behind it is that if I had two curves and I found the area, oops, my marker wasn't quite on there. If I found the area in red, and then I found the area in blue, if I subtracted the area in blue from the area of the red area, I would get this green remainder, if we want to call it that. And then really importantly, the joys of the smartboard here, if I take away the blue and the red now, we see that we get that green section. So the idea is that it's the area underneath the top curve minus the area underneath the bottom curve, and that yields this green area, which would be the region between these two curves. Now, we'll doctor this up with our notation just a little bit to make this as clear as possible. This is one of those things where if you can do 10.1, you can do 10.2. 10.2 just involves a bit of setup before you're able to actually use the antiderivative process. So on this particular diagram, this top curve, and again, in this case, we'd have a quadratic and linear. I'm going to identify, struggling with the marker today, that this is y equals f of x, the top curve, and then down here is y equals g of x, which we'll call the bottom curve. And then really importantly, we're going to be finding the region, I'll try to make these as vertical as possible, between x equals b and x equals a, and I'm just going to define that region right here, and that would be between those two curves, and I'll just label that with maybe I'll put a capital R. Now, I'd like to make that definition for R at this point too, that if we talk about how f prime is from f of x to g of x, then I can say that that region is going to be the antiderivative of f prime, which is capital F evaluated at b minus capital F evaluated at a. That's what we did in 10.1. I'll just put a 10.1 over here. The real only add-on in 10.2 is that we have to be able to come up with that f prime formula right here. And then once we know that, we can use our basically 10.1 technique to find that region. Now, if that weren't, complex enough, we can also get a situation where the graphs actually change. And this particular graph is a couple sinusoidal graphs. And what I'm going to do is I'm going to call this y equals f of x. And then the bottom one, to try to make this as clear as possible, I'm actually just going to run over the curve in red, because the idea here is that we see that the red function is not always below the black function. And so what we have to do in a case like this is we actually have to redefine the question and come up with two different regions. And the way that we would do that is, let's say we were trying to find the regions between these two curves from x equals a right here on the y-axis. I'll put a dotted line just so we can see it. And then all the way to, let's just go midway through here, and I'll label that as x equals b. Now, I cannot just say that that f prime of x is equal to f of x minus g of x, because f of x is not always on top of g of x. So what we need to do is we need to find where they intersect, or where they switch, that kind of top and bottom positioning, and I'm going to label that here as x equals c, and then I'm going to call that region 1 and then region 2. And the way that we could define those regions is I could say that R1 is going to be equal to, or let's put R1, and then we would do that by making a capital F prime of x, that in region 1, f of x is above g of x. So that f prime of x would be f of x minus g of x. And then what we could do is, to make sure we understand exactly where we would use that, I'm going to put the bound down here, and it's going to be from a to c. So this region 1 that I'm kind of just doing a little cross-hatching there, the function f is above function g, so we subtract function g from function f. If we look at region 2, and I'm going to label it as f prime of x again, because that's fine. In region 2, we would have to do g of x minus f of x, because g of x is on top, and that would be done from, c to b, because c is the lower bound of that second region there. Now, when you're doing this, to find the area then between these two curves, we could summarize that and say that the area is going to be equal to R1 plus R2. And in a question like this, we would have to find R1 and R2 individually and then sum them together at the end. Sometimes students struggle with finding that intersection point, but typically they're kind of easier functions to determine where they intersect. We talked a little bit on 10.1 that, negative area, at least as a kind of a calculus concept, is very possible. But when we talk about, they'll define that negative area is typically more used for net change, which we'll talk a little bit about at the end of the course. When we talk about the area, above a curve to the x-axis, then what we would do is we would use the x-axis as one of our curves. So I'm just going to label right here, and I'll actually give its function. This would be at y equals 0. And I'll just put maybe f of x above it, and then I'll label this guy as y equals g of x. If I wanted to find this region between the curve and the x-axis, to find that region, I would use f prime of x. And I think it's really important that y equals 0, which is f of x, is still on top. So it's f of x minus g of x. And we would do that from a to b. This would be x equals a. And then right here would be x equals b. That should be a square bracket. But we know what f of x is. Because f of x, we're using the x-axis, I would say capital F prime of x is going to be 0 minus g of x. And basically what this does is it takes the signed area that calculus would give us and multiplies it by a negative 1. And that's an important consideration, that if we're modeling a real life situation in the Cartesian plane, that negative area on our graph could very well correspond with, the amount of garden I'm planting in a parabolic planter, or, something along those lines. All right, let's do one of these. There's no substitute for, actually looking at these equations. This is actually the graph in the very first definition. So I'll just draw it again really quick. Y equals x squared plus 1. Just for notation's sake, I'm going to call that f of x. And then y equals x is going to be g of x. And I should have color coded that, but I'll do that really quick. I'll do that one in red, just so I can say red function and green function, or red function and black function. Oh, where is it? Line style? Oh, yes, we'll make that guy red real quick. Oh, it didn't like that. All right, the struggle is real, but we'll get there. So y equals x is going to be g of x. Didn't like that either. G of x, and then y equals x would be this red line right here. Like I said, that is the graph at the start of the notes. And then because we're looking at that region from x equals 1 to x equals 3, a lot of students want to find out the values of the functions, but we don't really need them. The calculus is going to do all that heavy lifting for us. So I'm just going to identify that x equals 1 is this blue line, and then x equals 3, and I'll put a dotted line there, is at that point. And then I am going to use just that same notation. I'll put that as capital R. Now, in order to find capital R, that region between the curves, what we are going to do is identify that we can do so, and I'll put an R up here. I am going to say that capital F prime of x, which is just a means to an end basically, is going to be f of x minus the red function because it's underneath, which is g of x. And then I want to add this in, that the area, or maybe I'll use R. There's nothing wrong with using R. We identified it as a region. I'll put right directly underneath here that the region itself is going to be equal to the antiderivative of f prime of x evaluated at the upper bound minus the antiderivative of that capital F function evaluated at the lower bound. If you're finding this notation a little bit tedious, there is some good news, because this will get a little bit easier as we introduce the actual integral symbol in calculus. But for now, we're just focusing a little bit on the antiderivative itself. All right, so I'm going to do two things here. I'm going to find out what capital F prime of x is. We said it was f of x minus g of x. So f of x is x squared plus 1, and g of x is just y equals x, so it's x, which means that capital F prime of x is x squared minus x plus 1. And this is where our 10.1, our antiderivative, kicks in, because now I'm going to say that capital F of x then is using those power antiderivatives, or power law antiderivatives. I'm going to have 1/3 x cubed minus 1/2 x squared plus x, and then just to make sure we remember, we need to include the constant of integration. That needs to be there. Now, it's kind of nice, because next, I'm going to say that the region is going to be my capital F function evaluated at 3 minus my capital F function evaluated at 1. Need a fair amount of space for these problems for sure. So that region is going to be 1/3 times 3 cubed minus 1/2 times 3 squared plus 3 plus a constant minus 1/3 times 1 cubed minus 1/2 times 1 squared plus 1 plus that same constant. All right, quite a mouthful. That's definitely a pretty long line of algebra happening there. going through this, I mean, this I hope is not going to be too much of a struggle. This is basically just adding fractions together. So I'm going to write a little bit of work here. I'm going to say that r is equal to 1/3 times 3 cubed is just 3 squared. So I get 9 minus 9 halves plus 3 plus a constant. I'm going to apply that negative. So we're going to be subtracting 1/3. I'm going to be adding 1/2. I'm going to be subtracting 1, and I'm going to be subtracting that constant. And that's something we looked at in 10.1, that those constants of integrations are going to cancel when we're using this antiderivative process for the area between curves. All right, I know you can add fractions or you can use the math frac button. If nothing else, you will get that region is 20/3, and then I am just going to put units squared. If the question gives you the ability to give the unit, you should do so. That gives the math a little bit more meaning. All right, I'm going to cut this into part 1 and part 2 at this point. So make sure you have done part 1 before part 2.